Great. So we are incredibly happy to have Francisco telling us about the Cosmohedra, who is a new postdoc on the first floor.
Yeah.
That way.
Yeah, right there. So hi everyone. My name is Francisco Vazāo. I started here in September, and I'm going to be talking about Cosmohedra, which is a paper by both Nima and Carolina. And then we can extend, so this is about the geometric description for the full wave function. And then with Carolina, we did an extension for correlation functions. Well, so this is the outline. The first two parts are really just a review, and then our work comes in this section. And if I have time, I'll do the extension for correlation functions. So the underlying setup is, well, we are interested in computing cosmological correlators, so these correlation functions at the end of inflation, which in principle can be measured in the CMB or in the large-scale structure of the universe. And well, one way to compute them is just integrating against the mod square of the wave function. And wave function, well, you could either look at one or the other object, of course, but that's shown to have really nice geometric properties. And yeah, here we're going to show you some of these. And schematically, this is one type of process we can look at, like single exchange diagrams. So well, we can define the wave function as the path integral, and the theory that we'll be considering is a theory for colors, scalars with cubic interactions. And well, and there's most of the time here I'll be talking about the flat space wave function. However, it's very easy to relate it to the de Sitter wave function for a particular type of states, which are conformally coupled states. So it's a particular value of the mass, where we can write the action as basically a flat space action for a flat massless scale in flat space with couplings that depend on time, and this would be the time dependent. So, and you can compute the wave function perturbatively, and these are and you expand it in these wave function coefficients, which admit a diagrammatic expansion. This will be like Feynman integrals, Feynman diagrams. I keep forgetting change that. And these diagrams, well, they have also an integral representation where we'll have a bulk-to-bulk propagator. Here will be this guy, and we'll have bulk-to-boundary propagators, which are this form. So, yeah, this would be the mode functions for massless fields in flat space, or conformally coupled fields in de Sitter, where then you have these time-dependent couplings. If you are working in more general massive fields in de Sitter, then this would be angle functions. But we can still relate the wave function from conformally coupled scalars to some types of scalars by acting with differential operators on the integrand for conformally coupled scalars. In general, in flat space, you can just integrate out time and you'll get a rational function. For conformally coupled scalars, you do a Fourier transform and just have an integral over a rational function. And from now on, I'll be talking about flat space wave function, but keep in mind that we can have this, we can relate it to other models like in this way. So these are a couple of examples of the types of once you do the time integral, the type of functions that rational functions that you get. So here, for example, the time already we see some simplifications. We would expect the bulk-to-bulk propagator as 3 terms, but in the end they simplify to this just 1. And here you would expect 9 terms for the bulk time integral, and they simplify to just 2 terms. And
that's what conformally coupled scale?
No, I'm just talking about flat space wave function. But I mean, if you want to write down the conformally the wave function for conformally coupled with scalars, you just shift the total energy coming into each vertex and integrate over this shift. So you'd have like an integral here over some shifts which appear in the couplings. But so I mean, from one integral you can easily uplift to conformal. So that's why I'm just talking about this. And there's some nice structure to these rational functions. Well, the first thing you can do is to try to identify what are these poles. So they can be related with the total energy in that is associated to the sub-processes of these graphs. For example, you have like, let's say, the total process, which we identify with this blue tubing. The total energy coming out of it is, well, it's really the total energy of the process, which is K1 plus K2 plus K3 plus K4. And that's the pole that you have in the rational function here. And then you have two more subgraphs, which are these 3-point processes. And for example, for one of them, for this guy, you have K1 plus K2 plus mod K1 plus K2 here. So it's the exchange momentum. And like this, you can identify all the poles in your rational function. For example, at 5 points, you'll still have the total energy, the single site tubes. We call these things tubes. And here you have like a 4-point process, which gives rise to these tubes. And you can identify all the tubes, all the poles like this. But you can already see at 5 points that the structure is not, well, it's not just one over all the poles. Like you will have some numerator. We just chose to decompose the rational function in this way. So next I'll tell you how to get the numerator. But these poles already have a nice behavior. For example, in parallel to scattering amplitudes, where if you go on a pole at this tree level, you get factorizes into left and left, the scattering amplitude to the left and to the right. Also, the wave function, we have a nice factorization structure. For example, if you go on the total energy pole, the amplitude shows up. The residue is the amplitude, and well, you can see this is just a computation for this process. If you take this to 0, then just recover the minus time of 4 points. And other poles will also have a nice factorization structure, which will be you will go to the scattering amplitude associated to the sub-process times linear combinations of wave functions. So what's the rule now to get the full rational function? Well, before I just told you how to get the pole, so to each two you can associate a given pole by just looking at the energies that are exiting the tube. To write down the full wave function coefficient associated to a diagram, you would consider the all maximal sets of non-overlapping tubes. We can call this a tubing or a rational. And then you just sum over those all of those sets, and that gives you the correct wave function. So a non-overlapping tube is anything that either is nested, like two tubes are one is completely contained by the other one. That's non-overlapping, or they're completely disjoint. If they're partially overlapping, then that's sets. And obviously, all the single site tubes and the total energy tube will appear in every single term. So in the examples below, I didn't write them down because they're always there. You can just calculate them out. So for this, I have 5 terms, and for the star diagram, you have 6 rational terms. Yeah. But so, what I want to tell you about in this talk is geometric description for the full wave function. So we have to come up with a language that puts every diagram in the same footing. So we can take a parallel with amplitudes where there's this very basic statement that, well, if you have momentum conservation, you can just write down this momentum polygon. And if you triangulate it, that will just be dual to a diagram, where you put all the nodes in each triangle, connect the nodes, and then draw the lines out of the outer edges. And the variables which will be dual to your propagators will be these these chords, like in this case x13, x14, and x15, which you can just write them out. Like this will just be the propagator. And this is for scattering amplitudes, but for the wave function, our poles will be sums of will be linear polynomials in the energy, so will be sums of energies. So our variables, you can think of them as perimeters of sub-polygons. So in this case, you can see that this triangle completely dual to this tube, which we already know what's the pole which corresponds to it. And here for the square, you have this 4-point process, and the pentagon will give you this 5-point process. And this allows us to generalize the Russian doll rule for the full wave function. You just, instead of saying maximal sets of tubings, you can consider all maximal sets of non-overlapping subpolygons. And if you do that, you'll find that there are 10. So the full 5-point wave function will be given by these 10 terms, and I organize them by column. So each column will be a Feynman diagram. So you have 5 in total. Just sum overall the triangle.
Go to the previous transparency.
Yeah.
So the one you had there in the middle, would that be included in the sum you had in the next slide? You have some polygon there in the middle.
Sorry, this is 5 points, and this one is 6 points.
I see. Oh, I see. So in general, you have things which are not triangles.
That's why it's asking. Yeah. So you'll have all the poles. You have to consider all the poles. So you have poles which will correspond to pentagons, squares, any.
Okay.
You also have the full polygon.
Okay.
The total energy.
For each polygon, you're supposed to multiply all the sub-polygons.
For each, so you consider like a maximal set of non-overlapping polygons. So for example, in this case, it's all the triangles, the square, and then the pentagon, and then you cannot draw anymore because they will be partially overlapping. And then you multiply all the poles. That's what you get for each of these terms.
Okay.
And it's written here.
Can I ask what's like the big picture reason why you're studying this?
Well, I'll come back at the end, but to that. But so, well, one thing would be nice to have just a description of the wave functions purely in boundary kinematics. Another thing, well, that's more of a
Compute contributions that we didn't know before.
Yeah, in principle, yes. Although what we can measure is very little, so I'm not sure. Computing 10 points will be particularly useful, but the point is that, for example, in scattering amplitudes, I mean, I'll show you right after, just after this, the discovery of Associahedron allowed like connecting scalar theories, like the NLSM and Yang-Mills. One hope is that this allows us to study a larger class of theories, not just colored scalars.
Well, I think what Andrea is also asking, like, I mean, are your calculations, are you calculating wave function? I mean, this is incredibly impressive. But I mean, are you, is this tied to observations?
Well, in principle, if you, well, not the flat space, because
Yeah, this is the case, for example.
well, you
But
usually
you have you have conformally coupled scalars, right?
that's also not, no, but we can all master scalars is also obtained. You can obtain it from here just by acting with.
Do you get the gravity?
No, just scalar modes. We don't. Yeah, I don't know. I'm not going to talk about any speech. Just scalars. But you can.
Is it really hard?
Spin.
Can you extend this formalism to anything that has like space?
It's just all the calculations get very complicated very quickly. I think
Technically complicated or
no, just very big, very quick. I think. For example, the graviton. I mean, you explain the action. The 4 points will be very.
no, it's yeah, no, I understand.
And so, I mean, what we need at the moment, I think there are some people working on like twisters for this for cosmological correlators would be a nice way to package such that the computation will get a bit more practical. I'm just talking about scalars.
I can provide a little bit of motivation,
Yes.
which is that you can get, even though he's working with conformally coupled scalars, that means you fix delta. You can act with differential operators on this thing to get a correlator where the external states have different deltas. So that's one way. I'm saying.
Always scalars.
What?
Always scalars, right?
Always scalars, but
Yeah.
then like there's an irreducible amount, like when you're doing this even with spin, like let's say I do the spin case here, like you do this tensor reduction formula and all this stuff, which is like algorithm is technically annoying, but it's algorithmic, like you can run it in a computer in finite time. But then there's like an irreducible amount of complexity, which is the graphs that he's studying.
Yeah, I mean, maybe I was clear at the beginning. You can act with differential operators that shift the mass value of your scalars. So you can obtain massless scalars from conformally coupled scalars, and those are physically more.
You're saying also that conceptually, these techniques also will allow you to better study like graviton correlators, they're just a mess.
Well, I mean, in principle, the pole structure should be similar, but there you also have all of the spin structure, right? That you have to package somehow.
I know you don't like lower dimensions, but can you do any of what you're doing to dimensions? And then we can like really like it's much better theoretical control, but the machinery is very strong.
I guess, yeah. I mean, I never said anything about dimensions, so you can just.
Oh. I thought you were
dimension one.
before.
But yeah, I mean, you can. Well, what would change would be. This one.
The propagator would change now a little bit, or like things would change.
If you're doing conformally coupled scalars, what would change would just be like this Fourier transform.
What's a conformally coupled scalar?
Master scale.
What's master
But yeah, the wave function, it would just change the measure. Line, that's all.
Thank you.
Very small technical question. Can you explain why this computation using sub-polygons is more efficient than the regular Feynman diagrams technique?
Yeah, I will show counting at the end, but well, already from Feynman diagrams.
Well, each one is one Feynman diagram, right? So each term there is one Feynman diagram.
That's the question.
Each term, no, each term here, sorry, it's no, each term. So for example here, so the term I was showing you was basically all the 5 Feynman diagrams that contribute for the 5. So it will be, so one Feynman diagram, each term there is just one of these guys basically. So there will be this guy, the guy that there will be one that gives you this part, and then there will be the other term that gives you this part. So each diagram will correspond to 2 terms. The thing is, if you do the integral, your Feynman, your bulk propagator has 3 terms. What's non-trivial is that already, for example, for the 4 points, you expect 3 terms, but some poles will cancel and it will simplify to this thing, to just 1 term. That's not obvious from the bulk planning.
In terms of bulk contractions, each polygon corresponds to 1 diagram or not?
You mean
It was a GVB construction.
no. So 1 diagram will give you 2 terms at 5 points, and here, for example, yeah, the 5 points will give you 2 terms. At 6 points, 1 diagram. In this representation gives you 5 terms, or the star diagram gives you 6 terms. The bulk, if you just naively compute the bulk time interval and simplify anything, you'd be computing, well, this guy is 3 to the 3, 27.
So you're organizing the results of computing Feynman diagrams.
Yeah. Or, I mean, this part, I mean, still reviewing. So this was already done by Nima, Benincasa, and Postnikov, where they wrote this cosmological polytope paper. And there it really shows how these simplifications happen. We're just trying to generalize this for the full wave function, this representation.
Let me go back to
Yeah.
the slide. That sum that is there is one Feynman diagram or all the Feynman diagrams?
This is all the Feynman.
The one in the bottom of the slide.
This is all of the Feynman diagram.
Okay, thank you.
This is the full wave function. Yeah, not just one. But here, yeah, but we're organizing in terms of sets of non-overlapping sub-polygons instead of Feynman diagram. But yeah, so in this case you have 10, but if these columns, each one corresponds to one Feynman diagram. And so the ABHY associahedron. So this is for scattering amplitudes. Well, the associahedron has been known for a long time. It's just a polytope that encodes the combinatorics of triangulations of a polygon. You can see here. So the vertices will correspond to different triangulations of the pentagon, or in this case of the hexagon. And well, the terminology is the following. Like, for example, these pentagons, we call them facets. The edges or codimension 1 faces. The edges are codimension 2 faces, and the vertices codimension 3 faces. And as you go in higher dimensions, well, there'll be higher codimension faces. And the way to think about this is, well, and if you were to build it, you just start with a partial triangulation, and you could add, there's two ways you can add another chord. So either go to this vertex or to this one. And then you could, from this guy, you could remove one. You are in a complete triangulation, so the only thing you have left to do is to remove a chord. If you either go back or go to this guy, and then you keep going until it closes. And then it's the same thing for 3 dimensions and so on. And this is just the definition that C prime is a face of C, if C is a refinement of C prime. Sorry. So if C is in C prime, meaning so C prime will be like this vertex will be a face of the pentagon, given that the number of chords and the chords in the pentagon are in this like that label this face, are some subset of the chords that are labeled this vertex. It has a very nice factorization structure. If you want a given facet is basically given by like a facet is labeled by one chord. So in fact, the structure of the facet will be that of an associahedron of the polygon to the left of the chord times the associahedron of the polygon to the right of the chord, meaning the associahedron for a 3-point for a triangle is just a point, and the associahedron for a pentagon we saw before, well, it's a pentagon, which is just a coincidence. So this facet will be a pentagon. For this guy, this splits into 2 squares, so only the associated two times the associahedron of 4-point, which would be 2 segments, so this becomes this is the square. This is exactly the type of factorization structure you have in scattering them. So the ABHY realization is, the way you define a polytope is you either define its facets or define its vertices. Here we define its facet inequality, so it's just a hyperplane inequality. But for example, for 6 points, I showed you there was a 3-dimensional polytope. There's 9 internal chords in total. So we have to go down in dimension, and for that we pick preferred triangulation. You can pick this one, x13, x14, x15. And and then you write down all the other x's in terms of the x's in the preferred triangulation and your non-planar variables, which will be just, these are just pi.pj, pi being, and the associahedron lives in the space where you fix these c's to be some constant, any positive constant must be positive. And from there, well, you can extract the amplitude by, well, from the canonical form of the polytope, canonical form. So to any polytope, you can associate the volume form, which is defined if you take a residue on one facet, it must get the canonical form of that facet. So here, if I were to take the residue on the canonical form on this pentagon, I should get the canonical form for a pentagon. That's all I'm saying. And the maximal residues, if you go on the vertex, should be either plus or minus 1. And if you have a simple polytope, meaning, so the vertices have at most, if it's a d-dimensional polytope, your vertices have at most d facets meeting. So here you see that every vertex only is met by 3 facets, so it's simple. You can just compute it by, the canonical form can just be computed by, for each vertex you multiply the singularity that you associate to each facet that meets in the vertex. And the singularity are just the chords that label the facet. And that will give you the scattering. So now into Cosmohedra, before we go to the full wave function, I said already that there was a description for single graphs, a geometric description for a single graph, so the cosmological polytope. Over that one, I will not talk much about it here, but not very obvious how to glue them together, sort of, to describe the full wave function. So one natural thing you can do is try to find another description for single graphs. And well, the most obvious thing one can do is label the facets by all the tubes. So meaning all the poles that you have in your wave function coefficient. And 2 facets will be compatible if they are met, if they correspond to 2 non-overlapping tubes. So here, the mutation that you could do, you can either, to these 2, you can only have 2 non-overlapping tubes with either this 4-point or this other 4-point. Maybe it's not super clear. So let's say you go to this vertex, and there's only one choice. You're already at the maximal set of tubes. Then you can just go down to this guy and keep constructing like this. And it turns out it closes. Maybe at 2 dimensions it's obvious, but when you go to 3 dimensions, well, everything still closes into one single polytope. And here, yeah, each vertex will be tubing. So each vertex will be one contribution to your wave function. Now in this case, we're just talking about single graphs. It has a nice factorization structure as well, like similar to the associahedron, where it's just the graph associahedra that we associate to the sub-process, the tube, times the graph associahedra that you get from the graph, from shrinking the tube to a point. So yeah, this guy will be an hexagon because this is the star, the graph associated of the star will be an hexagon, and if you shrink this to a point, then you get a 2 chain, whose graph associated is just a point. So it's a point and an hexagon, you get an hexagon.
These associahedra, are you telling us that they're relatively easy to see what they are, and they're simpler to use that and see what are the tubings that have to sum over instead of actually trying to label, list all the graphs? And is this an efficient tool for finding which diagrams to sample?
Yeah, once I provide the embedding, and I will show you also how the counting works, but yeah, this is, I would say, faster than, because here, I mean, for a wave function, it's not just that you have to look at the graphs, like each graph will have many terms in it, right? So each, or scattering amplitude at tree level, for this theory, each graph will just be 1 over the propagate, so it's just one term. But here, like I said, one graph will be the sum over several rational terms. Even from the bulk integral, that those even will be even more terms.
But this is the way to organize those.
Yeah, this is one way to organize this.
It's simpler than actually drawing all those tubings.
Yeah. But
Because you might forget ones, and here you know that you can't do everything.
ideally, yeah, I mean, at 2 and 3 dimensions you can draw, but then once you go higher, you cannot draw anymore. So that's why this embedding I showed for the associahedron, I showed an embedding. I'll also show for these ones, where you just provide the facet inequalities. So you just give the facet inequalities, so there are just linear equations to polymake, which is the software that can compute polytopes. And then it will tell you anything you want to know about your polytope, what the facets look like, how many vertices are in each facet, everything you can think of, it just gives you. And it's quite fast. And yeah, then it's very easy to extract the wave function from there. But all you need to do is just give the facet definition. You don't need to think about like how you nest tubings. Because that if you do that, then you're not really gaining. That's a very lengthy process. But yeah, if you just give the facets, a software like Polymake can just give you all the combinatorics that these facets have. So the Cosmohedra is well, basically the same, but as I showed you before, instead of for tubings, well, we have to consider sub-polygons because we want to talk about all the graphs at once. So the way you can build it, if you at least at 5 and 6 points where you can actually draw, is just each facet will be one. You can start by this grid facet, for example, which is just a tiling of the momentum polygon. You always have to have full tilings, meaning you cannot have just one square. It must be filling the full momentum polygon. And then you can go up in codimension of the facet, meaning you go from an edge to a vertex by either adding one level, sort of one more polygon, such that your nesting increases until you reach a vertex. In this case, there's just edges and vertices. So in this square, there's two things you can do. You can triangulate the square 2 ways. So you can either have 2 triangles and go here, or 2 different triangles and go to this vertex. And from the vertex, you can remove a square, or I could remove the triangle inside the square, but then it would be going back. So if you remove the square, you go to this facet, and you will reach another full tiling of the momentum polygon, which in this case looks like it's like a full triangulation. And you can keep going, and it closes. And you can see one thing, if you decide to, for some reason, label them by chords, that this is really just like you're shaving the associahedron. So before, in the associahedron, a facet would just be labeled by a single chord, and a vertex would be labeled by a full triangulation. But here, we're labeling things in terms of levels of nested tubings. So there will be facets that you can think of them as associated to full triangulations, and others which will associate to partial triangulations. So the association for this thing was a pentagon, and we shaped all the vertices and got a decagon. So I showed you before the sum of those 10 terms, and so you have to be the decagon.
Let's see the thing on the left, right? So each of these figures represents one Feynman diagram.
No, this represents a full wave.
Each of the edges that represent one Feynman diagram. No, on the other side first.
Yeah. In this case, the red ones would
represent an angle. I mean, for example, the green edges, the diagrams that contain Cosmic functions for point vertices.
There would no. I mean, you think of the red ones as full Feynman diagrams, and these ones are just partial triangulation. They contain contributions from different Feynman diagrams. So in this case, would be, I guess, like I wouldn't call it a 4-point function, but they just contain contributions from different Feynman diagrams. And for 6 points, now compared to the associahedron, it grows in complexity because you have to shape every single vertex and every single edge into a facet. So you have a lot more facets. But the combinatorics is always the same. Every facet will just be corresponding to a single tiling of the momentum polygon. And you go up in codimension by tiling the sub-polygons inside. Like you can start with this pentagon, and you can fill it with a square and a triangle, then you come to this edge, and then you can fill the square with 2 triangles. So you go to sort of the third level and you come to the vertex. Or you could also fill it with a different square, a different triangle, then you come to this edge, and then fill the square with a different triangle, then you come to this vertex here. And for example, these 5 guys would contribute to one single Feynman diagram, or the contributions from one single Feynman diagram. So at 6 points, I mean, I showed you before that there's 5 contributions to the 6 points wave function or one diagram for the chain graph. But the star graph, which is this topology, there will be 2, will be an hexagon, and that's what. Yeah. It also has a nice factorization structure where each facet now factorizes into the Cosmohedron of the left of the chord times the Cosmohedron on the right times the graph associahedron that you get from putting 2 nodes into each sub-polygon. So like this guy would be the Cosmohedron of the 5 points, which is a decagon, times the Cosmohedron of the triangle, which is just a point. You get a decagon. Yeah, like I said, you need to get the embedding for it. So it's facet description, so that we cannot, is the simplest way to actually extract information from it. And here, I mean, the natural way to do is maybe go. So I said before that you get the Cosmohedron by shading the associahedron. So, for example, if you start with a 5-point associahedron, like the covectors associated to the facets, you can think of these, and we want to sort of shade this vertex. So the natural thing to do is to add another facet with the covector being x13 plus x14. But that will only define sort of the direction of the facet. So you need to add some constant. Sorry, call epsilon 3, 4, which sort of parameterizes how much it shapes. So if this is too big, then it will completely shape the associahedron. If it's too small, it's not even going to shape anything. And that's what we write here. So we will have the normal facets of the associahedron, which are just a single chord bigger or smaller than epsilon. Or we have new facets, which are just linear combinations of the compatible facets. One side and the other, so it just be a sum. Like at 5 points, you get just x13 bigger than epsilon, x13 plus x14 bigger than epsilon, and the same for all the other possible chords. So now the question is, how do you find these epsilons? Just demand that a single vertex exists. So if, for example, here you demand that this vertex exists, that saturates 2 facets, this one and this one. And then you can easily obtain a constraint on the epsilons. I think I forgot to say before is that for the Cosmohedron, we have non-simple vertices. So here, this guy has 4 facets meeting it. So it's non-simple. To be simple, you have to have 3. And that will give you too many constraints and forces an inequality on the epsilons. And so right now we know the constraints on the epsilons, but what really are the parameterizations that satisfy these things? On natural, so an epsilon is labeled by the chords that of the facet it is associated with, right? but you can also label a facet by polygons, sub-polygons. So you just map the epsilons to the deltas of to a sum of another sum of constants, where each constant is associated to a sub-polygon. And this automatically satisfies the equalities, and it reduces the inequalities a lot into this form. And they're very trivially satisfied by a convex function. And here's an illustration of what these inequalities look like. You associate the delta, for example, with this square, this other square, then the intersection will be this triangle, which also has a delta associated to it, and this union is a pentagon, which has another delta. So in the end, all you need to do is write down your inequalities. You impose the ABHY constraint, meaning you write the x's in terms of these non-linear variables, and you have to pick a base triangulation. And the epsilons, you just map them to these deltas, which are parameterized by this function. So if you just input this, then you get an embedding for the Cosmohedron, and then you can read off the wave function. So the counting is the following. For the associahedron, which basically encodes scattering amplitudes, the number of vertices, meaning the number of Feynman diagrams, grows exponentially. For the Cosmohedron, well, also the facets, some of them will be Feynman diagrams, also will grow exponentially, but the number of vertices, meaning the number of contributions to your wave function, go factorially. So at 9 points, like a scattering amplitude will have like 400 terms, the wave function will have like 78,000, and it goes very, very fast. And we can generalize this for loops. It's almost everything just follows through. The only thing you have to consider is that now instead of a momentum polygon, we consider a surface with a punctured disk. Instead of sub-polygons, you consider like subsurfaces of this punctured disk. But the overlapping rules, everything follows just the same. To extract the wave function, well, it will not be a standard canonical form because we have these non-simple vertices. So we have to provide a different rule. Let's say this is the not so nice part, but still one can get the wave function by just blowing up every single non-simple vertex by turning these equalities into inequalities, and then for each facet, the singularity we associate is just a sum of products of any two sub-polygons that meet at a single edge, and then you compute the canonical form of this the standard way and keep just the simple poles and sort of truncate the canonical form, and that gives you the wave function. But so now I'll say I'll this generalizes to correlation functions. I said at the beginning how you compute the correlation function. Just integrate one way to integrate against the mod square of the wave function. So that would look like this. And you can think of this as like an action with infinitely many terms. So the correlation function will just be, well, so where the vertices will be wave function coefficients and the propagator will be the 2-point wave function. So it will just be twice the real part of the wave function will just be like two times k, which is the momentum running in the 2-point wave function. So for example, a 5-point correlator will just be the 5-point wave function times a sort of an exchange graph, which will be the 4-point times 3-point over the momentum you cut. Here we represent it diagrammatically like this, where the red sort of cutting the propagator is what shows here. And at most you can cut 2, so you get a double exchange graph, which will be a product of 3-point wave functions. And yeah, so now the total energy is no longer a pole of the full correlator, it's just of a single term. For example, for this 5 point will just be pole of this guy. So we can no longer factor out at a single graph level. But the natural thing to do is to consider all the poles just like before, where now the compatibility will just be given by the fact that these cuts cannot cut a 2. So this guy is incompatible with this one because we'll be cutting it. And all the contributions to the correlator will just be given by the vertices of this. So this is just the standard graph associahedron for this graph. And these ones will be the new contributions that only appear for the correlator. So there will always be a facet which will be the graph associahedron. And this is what it looks like for 6 points, where again, this facet is the hexagon, which is what the graph associahedron saw for the star. And for the full correlator, it sort of generalizes in exactly the same way. Where again, now consider sub-polygons and chords. Those will be propagated the new poles that we have for the correlator. And the embedding is pretty much the same, but now we sort of tilt the Cosmohedron facets by some vector like this, and so at the bottom we'll have the Cosmohedron, at the top we'll have the Associahedron, although these vertices don't contribute, so we send this facet to infinity, and then the embedding is just the same, where you have the new epsilon inequalities, but they are also satisfied by the convex function I gave before. You can just extract the correlator pretty much in the same way as the wave function. And everything follows exactly the same for correlators. One loop for the one loop correlators. And well, now I'll conclude. So at least one takeaway I hope is that, well, this gives you that you can find the wave functional correlators purely from boundary kinematics. It would be nice now to generalize to a larger class of models, not just IQ. And well, we know how to put everything under a single integrand, get conformally coupled scalars, and from there get massless scalars. And then a nice prospect, I already mentioned it before, was that the Associahedron gave us a way to represent scattering amplitude from a stringy integral. You take a limit and you obtain back the scattering amplitude. And that eventually allowed for a connection between scattering amplitudes of scalars and the NLSM or supersymmetric Young-Mills. And it would be nice to see if we can draw these connections also for the wave function in correlators. And that's it.
Any more questions for Francisco? We already a lot of fun during your talk, so we have you around. Thank you so much.
Thank you.